All right. Welcome to Applied Statistics. My name is Paul Klawinski, and this is what I look like. Open up R. Start yourself a new file. I also don't have to shout anymore, so I should probably tone my voice down. Just start yourself a new R script. In this new R script, you can either do install packages and install swirl, or you can do it over in the install packages section, where you can just click on install, type in swirl, and it will give you that to go on. Once you have installed swirl, go ahead and load swirl. Using the library command. And then what you should see is you should see it that your console will start talking to you. So down here it says, "Hi, type swirl when you're ready to begin." So let me know when you've gotten this far. Anybody not gotten this far? Karis is still working, it looks like. Yeah.
I don't know how to get in this package. It's asking me to do.
Do you want to install? Yes, the answer is always yes.
Yeah.
Because you trust R implicitly. I say that kind of sarcastic, but also kind of true. Yeah, almost always when you're in the presence of an install, when you're in the process of an install, and they ask you a question, just say yes.
All right.
Yeah, no, you don't need to for this. This is a package that was designed by some really altruistic person, in that it has a set of tutorials that take you through many of the base functions of R. We did some work in R early, and then we went away from it, and then we did some more work in R, and then we went away from it. This coming week, we're going to be doing a lot more in R, and we're going to be doing it on a much more regular basis. So I want you to do some of the tutorials in this package to just kind of get us all back on the same page where R programming is concerned. My advice to you is that as you're working through these tutorials, that you keep a pad and paper beside you. You might even want to have a notebook, a spiral bound notebook, or a bound notebook, or anything that kind of keeps your notes together. Because I'll run partway through one of the tutorials with you today, and the tutorial will show you a bunch of stuff, a lot of which isn't particularly useful and that I don't ever actually use. But there are things that I find myself using quite a lot, and it would be nice if, as you are going through the tutorial, when you see things that seem useful to you, you write down what those commands are, so that you begin to make a list of useful commands that you will use in your own R work as you move forward. Are we all together? Right here? Okay. So type swirl, because we are definitely ready to go. What shall I call you? Put in your name. This is a strangely encouraging bot. It will give you words of encouragement occasionally as you work through the tutorials, and I find it a little unnerving. But anyway, the three dots. Whenever you see the three dots, that's your encouragement to just basically hit Command and Return or Control Enter when you are on a Windows machine. So you definitely want to continue working. So yes, let's get started. Oh, it gives you some instructions on how to get out of the program. So you can actually save your progress through these tutorials if you want, And so it gives you instructions here at the beginning on how to do that. So what we want to do is we want to just go to Unit 1, which is R programming, which is the basics of programming. So select 1, and we want to just go to R programming. Hmm?
Oh, Command Enter. Okay, never mind.
Yeah.
Okay.
Yep. Yeah. Hmm? Let's see. Da, 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 da. Did you select 1?
No, I didn't.
Yeah, select 1 to continue. And now the 3 dots mean to hit enter. Yep, there you go. And hit 1 again. So all of you should be at this point looking at a set of menu items. Do we all see this? No. You want to go to 1, so press 1.
Do I have to press it in?
It doesn't matter. It'll take it either way. Yep, now you're there.
It's not enter 1. I've gone to here. I just now got to this. Sorry, that's me
No,
to
yeah,
restart my
yeah.
session.
So do Control Enter, because that's what 3 dots mean. Now press 1 to continue, and enter again. Control Enter again. Now press 1 again, and that should take you to the. Oh, press 1 again, and that should take you to the. Yep, there you go. Yeah.
Press 1 on this one too.
Yeah.
Okay.
Yep. Yep. Everybody see this? No, not quite everybody.
It only has 5 options.
Yeah, you want 1. You want the first one. Now you want. Oh yeah, there you are. Now you're with us. Basic building blocks. Yeah, there you go. So everybody see this menu now. Okay. What I want you to do between now and say next Wednesday, but this weekend would be a great time to start on this. I want you to go through number 1, number 2, number 4, 5, 6, 7, and 12. 1, 2, 4, 5, 6, 7, and 12. So these are all things that we're going to be using pretty quickly here. Get some basics under your belt. We've already talked a lot about workspace and files and how to deal with knowing where you are in your computer, how to import files and how to work with files, how to see what's in your file space and things like that. This will just reinforce those things that we've already covered. Vectors are what they call the columns in data frames, and so manipulating vectors is something that we've done a tiny smidge of, but we haven't done a ton of, but this will get you up to speed on that. Frequently, we see data frames that have missing values in them, and oftentimes missing values will mess up your analyses because when R sees a missing value and you haven't told it explicitly what to do with those missing values, it just cancels your analysis altogether. So knowing what to do with missing values is actually important. Sometimes you don't want to look at the entirety of a data frame, and so what you want to do is you want to make a new data frame that is a subset of a larger data frame. And subsetting can be done in a variety of ways, and knowing the different ways to do it is useful. So subsetting vectors is a useful set of skills to have. Just a general tutorial on matrices and data frames, getting to know what data frames are, how they're constructed, how to work with them. And then the last thing is looking at data, right? Yeah, 1, 2, 4, 5, 6, 7, and 12. Oftentimes, the first thing that you want to do when you have a data set is you want to take a little peek at it and see what it's like. And so this works with the base R functionality. So we have base R, and then we have graphing functionality in ggplot2. You guys will be using ggplot2 almost exclusively for everything you do in this class, but there are also just base R kind of mapping functionality that is useful, especially if at the beginning of a project, when all you want to do is get an idea of what the data look like. You don't necessarily need those graphics to be pretty, to be publication quality. not your final graphic that you're going to turn in as part of your assignment. You just want to take a gander at the data and see what they look like. Base R graphics are fine for that, but you wouldn't want to necessarily show those to the world, so to speak. So let's click on 12. So let's type in 12. Let's go to looking at data. So whenever you're working with a new data set, the first thing you should do is look at it. What is the format of the data? What are the dimensions? What are the variable names? How are the variables stored, et cetera, et cetera? Are there missing data? Are there any flaws in the data? So hit return again. This is going to teach you this, and they're going to use a database from the U.S. Department of Agriculture. They've stored the data in a variable called plants, so use ls, open parentheses, to list the variables in your workspace, among which should be plants. If you just open this up as a new file, the only thing that you really have loaded is plants. You can see over here in your global environment pane in the upper right-hand corner that you have an object called plants. It has 5,166 observations and 10 variables, and that's the only thing in there. What the ls command did was it basically said list all of the things that I have open, and all of the things that you have open at the moment is just the plants data set, the plants data frame that this package opened for you. Yeah, so they give you encouragement. Excellent job. You got to see what was open on your computer. Yay. Now, you didn't need to use the list command because you can see what is in your environment right here in the environment pane. So, once again, I don't use the list command a lot because I generally know what's open because I can always see it in this pane. So there are going to be some commands that you're going to look at and say, well, I'm not ever going to use that. So don't write that down and keep track of it. But then there are other commands that you might see yourself using in the future. Write those down with a little note on what it is that those things do. So then it gives us class plants. And so when you type in class plants, it tells you that this is a data frame. Now class is a command that I use quite a lot, because you can do it on something like this where it's a data frame, but you can also do it on the columns. So if you run an analysis, and let's say that in an analysis you have labeled your treatments, treatment 1, treatment 2, treatment 3, treatment 4, and treatment 5, and then you go to do an analysis of variance on that, your analysis of variance won't run. And the reason that your analysis of variance won't run is because R is viewing that not as a character or a factor, it is viewing it as integer. And it's because you're basically just using numbers to serve as placeholders for a particular name. This could have been, control, but in your data set when you coded it as a 1. Well, when your ANOVA doesn't run and you don't understand what the error message is, one of the things you might say is, you might say class, plant, $, treatment. And what you're basically saying is, what is the treatment column in the plant data frame being classed as? And it will return to you integer. And what that tells you is, oh, I'm asking it to do an ANOVA on something that R is not treating as a factor. It's treating it as a number, and it won't do that. And so you then have to tell it to change plant $ treatment into something new. You need to treat it as factor. And what you're basically saying is treat as a factor this column in my data frame, and then save it just as that column. And then when you run class again, It won't return integer, it will return factor, and then your ANOVA will run. So I use the command class a lot because sometimes R doesn't do what I want it to do, and oftentimes it's because it's treating data in a way that I don't want it to treat data. Yeah.
So I was just say, like, so class basically just tells you like what type of data it is.
Yep. So it'll be numerical. It could be integer, numerical, factor, character. There are a number of different things, and generally when you're running an ANOVA, you want your treatment names to either be a character or a factor. Yeah. One of the things R has taught me is don't ever make a factor a number. just give it a name when you put it into your data set originally, because then you don't have to go through this stupid step. So this, if I was keeping track of things in a notebook, I would put down class as a useful thing to have in my toolkit of commands because it's useful. It can be used on entire data frames, or it can be used on vectors within data frames, the columns within a data frame. So hit return. You can use the dims column, the dim command to tell you the dimensions of your data frame. And in this case, what it's going to give you first is the number of rows, 5,166, and it will give you the number of variables, which is 10. I don't generally use the dim command. Why not? You can see it up there. Up there in your right hand pane that shows your environment, it tells you what the dimensions of your data frame are. So you can run dim and get the dimensions, but you don't really need to because you have it up there. Hit return again. You can also use in-row plants to give you the number of rows. But once again, you already know that it's 5,166 because you can see it up there. And you can use in-call for plants, which will give you the number of columns. And there are 10 columns. One thing I never use is object size because I don't really care how big my total data set is because I don't know what I would do with that information. But this is 745,944 bytes. The only reason that you might want to do this is if you're dealing with really gigantic data sets. So if you're in biology and you deal with genomic data sets, you have DNA sequences that are, in some cases, millions and millions and millions of base pairs of data, and those data sets can get really large, and at times you won't be able to run those on your laptop. You would have to run those on a supercomputer, on a server farm at your university. And so when you have a program that doesn't work because your file is too big, it might be nice to know how big your file actually is to get a handle on why something isn't running. For most of my work, I don't ever have data sets that big, and I can't imagine that you're going to encounter data sets that big, at least while you're here at Jewel. If you get out and go to work at a place like the Texas Parks and Wildlife Department, for example, a couple of weeks ago I was talking to some guys there. They have a 40-year-old data set of people who have been collecting trapping data on amphibians or reptiles for 40 years, and they do it every year. Every year they run these pitfall trap arrays, and so they've been gathering data for 40 years, and they've never stopped to analyze it in 40 years. So they have this dusty data set that they keep adding to each year, but they would like to know what's going on with it. And I haven't looked at that data set, but I have that on my list of things to do. That's probably going to be a really big data set simply because it's 40 years worth of data. Yeah, Blaine.
I was just going to say, why would you have a data set that you store data for years?
Well, because you have technicians who are taking the data, and there's nobody at the Texas Parks and Wildlife who is in charge of taking that data and doing something with it, and so it just kind of falls through the cracks. The people who are currently taking the data probably don't even have any idea why the original people who were taking the data started taking the data. But the cool thing about the data set is you now have this 40-year-old data set on amphibian and reptile abundance at, I don't know how many, they do this at wildlife management areas across the state of Texas. So you have 40 years of data on animals that are ectotherms. An ectotherm is an organism that gets its temperature from the environment. So amphibians and reptiles, they don't moderate their body temperature the way we do by burning up a bunch of sugar and keeping ourselves warm. They have to get warm by going out and basking in the sun and things like this. So they have this data collected at a number of different wildlife management areas around the state of Texas for 40 years. Well, in that 40 years, the temperature has gone up an average of almost 2 degrees centigrade. What they're finding in their traps may have changed over those 40 years of time, and they actually don't have any idea because nobody's ever stopped to look at the data. So it could actually be a really kind of cool data set. Yeah.
Sorry, should we be typing up top or down low? Where you're
It doesn't matter either way. It'll work either way, as you can see.
Right.
I'm typing up top. Well, I started typing up top, and then I started typing down here.
Right.
It doesn't matter.
I was just wondering if there's a difference. Or...
No.
Okay.
Same thing.
It won't mess it up at all if I do the like number sign for notes as I'm filling it out.
Yeah, you'll want to do that in the pane up there, so
Right.
you save it. Yep.
Right, just to make sure that way I don't.
Yeah. So, but also it gave you instructions on how to save your place where you are, so you don't have to go all back through this. So this is how these tutorials work. They just take you through this stuff. So yeah, if you wanted to do what Blaine is doing, which is to save all of this work and make notes and stuff, you would want to be working in the editor pane up here rather than in the console, but it doesn't matter. It works either way. You might want to know what the names of the columns are. Whoa, what happened? Oh, because I didn't give it the data frame name. So ask for the names in the plants. And what it basically says is you have the scientific name, the duration, the active growth period, the foliage color, minimum pH, maximum pH, minimum precipitation, maximum precipitation, how shade tolerant it is, and the minimum temperature that it works at. And so this tells you what the names of your columns are. You might want to see what the data actually look like, but you don't want to see all 5,166 rows. And so this suggests that you do something that we've already done a number of times using the head command to see the top of the data frame. Whoa. And what that gives you is it gives you the scientific name, it gives you the duration, whether it's a perennial or a annual, the active growth period, spring and summer. But one of the things that you see is that there's a bunch of missing data in this data file, which is why you want to know what to do with missing data, which is why I want you to go and do the tutorial on missing data. So this basically just takes you kind of through how to look at your data. Yeah.
Head just shows us the top 6.
The top 6. Tail shows you the bottom 6. So you could also do, I don't know if the next thing is tail. Let's see. Oh yeah, so it's just telling you that you can do plants and I guess 10. Once again, I've never done this. Oh yeah, so if you do plants, 10, it gives you the first 10 rows rather than the first 6. The default is the first 6. But also useful is to do tail, plants, which gives you the last 6. And so you can look and see that your data set actually is 5,166 lines long. So anyway, head and tail is pretty useful. You will see me using that a lot when we go through data sets. So write down head and tail and write down what they do so that you can do this in the future, so you can refer back to it. I find a command much better which is STR, which stands for structure. And this is nice because it tells you a lot more than any of these single commands does. It tells you actually everything that all of these single commands are. It tells you that plants is a data frame. It tells you the dimensions of the data frame, 5,166 rows and 10 columns. It tells you that the first row, or the first column rather, is the scientific name. It's character data. And these are some examples. These are the first examples of the things that are in that column. The second column is duration, which is once again character data. It has either missing data, annual, or perennial. Annual is a plant that only grows a single year. A perennial is a plant that grows year after year after year. Active growth period is character data. Foliage color is character data. pH is a number. pH is a number. Precipitation is an integer. Precipitation is an integer. Shade tolerance is a character. The structure command tells you everything you could possibly want to know about kind of what is in your data set. So I find myself using structure way more than any of these other single commands because it gives me all of the information all at once. If you find structure to be useful, write down structure and write down what it does in your notebook of R commands. So as you work through these tutorials, be asking yourself, do it in an active way, ask yourself, is this command that the tutorial just asked me to execute, is that a command that I can see being useful in the future, or is it a command that I probably won't use very much? If so, take notes on those commands that are going to be useful and then disregard anything that is not particularly helpful. Questions? All right, close out a bar. I didn't read the instructions on how to save your progress through the tutorial, although you can scroll back up and see. So in your console, scroll back up and see where it was. It gave you instructions on how to exit if you want to save your place in the tutorial. And I just don't remember what the command was for doing that. I will occasionally work through tutorials myself. So I've been doing this for a while now. But one of the things that I'm not particularly good is manipulating data frames. I usually enter all my data outside of R, and so I usually organize my data frame in a way that I know that R is going to like it when I pull it in. I'm currently working on a data set that I did not gather myself, and the student who gathered it basically arranged the data in Excel spreadsheets in ways that I would not have. And rather than going back through and re-entering all of that data, I'm manipulating it within R. And so it involves filtering the data so that I filter out certain rows of data on the basis of a value in one of the vectors. And then I'm combining that data with the data that are in another data frame. And I'm not particularly good at doing those types of manipulations in R. So I've actually been looking at tutorials on data manipulation to hone my skills in those areas. Anybody who's working with R can always learn more things about how R does things. So I'm not asking you to do anything that I don't do myself periodically, which is taking tutorials. There's a guy named William King. I think his name is William King. He's at Coastal Carolina. When I first started learning R about 10 years ago, I didn't have clue one, how R operated or anything else. I had been using other statistical packages up to that point in my career, and I found his set of tutorials super useful and helpful in me teaching myself how to operate R. I have never taken a course in R. I am completely self-taught, so as a result, The things that I've needed to do as part of my work, I know how to do really well. The things that I need to do in order to teach this class, I do really well. There's a whole universe of things that I don't know about simply because I've never had to learn them. It's not the best way to go about learning R, but it works well enough, I guess. All right. I asked you guys to analyze this data set right here. How did that go for you? What questions do you have having approached that? Claire's got her printout. Everything turned out the way it was in the thing? Ask now, because there are at least a couple of you who on the test didn't do particularly well on doing chi-square analyses, and I can only guess that that was because you didn't ask enough questions in class when we were going through that in class. Generally, the test scores were pretty good, but there were a couple of you that really struggled with doing chi-square analyses. Any questions on the mechanics here? Yeah.
So we have to do the among, within.
Yep, so you have to calculate some squares among, you have to calculate some squares within. For doing either of those things, the first thing that you have to have is the mean, because some squares among is comparing the mean to the grand mean, and some squares within is comparing the mean to the individual values. So the first step is always getting the mean, and then to get the sum squares within, it's just the sum of square deviations of the individual values from the sample mean. So that's the beginning of the variance estimate. This is just 75 minus 70.1 squared, 67 minus 70.1 squared, et cetera, et cetera, et cetera. That should all add up to 142.9.
So, okay, yeah.
So then,
for SS within, though, it's every single observation minus its particular sample
mean. So this is minus 70.1. This would be minus 59.3.
Right, and then all of those sums of squares added together, all 50 of them.
That plus that plus that plus that plus that. This is sum squares within.
So it's
Yep.
all sums of squares.
Mm-hmm.
If you added them 50 numbers together.
Yep. Yep. But the mean that you're comparing to is the sample mean. For some squares, so that's some squares within. For some squares among, it's 70.1 minus the grand mean, which is 61.94 squared. So give me a minute. Boom, chicka boom. A little bit of rounding error. You can do an ANOVA by hand. There's nothing in an ANOVA that you can't do by hand. This is the difference between that and that is 8.16. 8.16 squared is 655.8533 with this 4 significant digits. So it's 65.5853. And then you multiply that times the sample size because the sums of squares among is weighted by the sample size. It's n times the mean minus the grand mean squared, which gives you 655.83, which is not far from 660 5.85. This was done in Excel where they carried out more decimal points. Obviously, mine's going to be a little bit off because I'm a human. Yeah.
So, but when you multiply the n by that's n by the entire thing, or
It's so this is the mean minus the grand mean. Mean minus the grand mean is this. This is it squared, and then I multiply that times 10 because there are 10 observations.
10 observations?
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this turned out. Whoa! How did I get?
But the only time that you multiply the n is for among, right?
For among, yes.
That's the only time.
Not the only time. So I didn't talk about the grand mean. How can you calculate the grand mean? Two ways you can calculate the grand mean.
You can add all the means together. Number of
Okay, so one way to get the grand mean is to take all of this thing and add it up and divide by 50. Sum of all the x values divided by the total sample size, which is 50. The other way, which Blaine mentioned, is you can do it based on the means. So this is what Blaine said. The mean of the first treatment plus the mean of the second treatment plus the mean of the third plus the mean of the fourth plus the mean of the fifth divided by 5. That only works on this data set. Would that work on this data set? You have different sample sizes for each of those, okay? So in this case, you can do this because everything is the same sample size. If they were different sample sizes, you would multiply each of these times their sample size.
So the reason we don't have to multiply and for the within numbers is we're just doing every single observation, so it's regardless of sample size.
What's that?
So I'm saying the reason we don't have to multiply ends for the within.
Within is that's already factored in to it.
I'm saying
Yep.
we're just doing every single one,
Yep.
regardless of the
Yep.
sample size of that particular.
Yep. Mm-hmm. So, and then in this case, you would divide by what your total sample was. So this would be 10 times 70.1 plus 10 times 59.3. But then this would all be divided by 50. So when you calculate the grand mean, you also weight those things by sample size, which doesn't matter when all of your samples are the same, but it matters critically if your sample sizes are different. And the reason is that in the next example that will work, for the grand mean, now I have to erase the screen. If I'm going to calculate the grand mean, this column of numbers contributes a lot more to the grand mean than this column of numbers does because it just has more data in it. So you have to weight those things by sample size, which is why you weight it by sample size when you're calculating the grand mean, and also why you weight it by sample size when you're calculating the sums of squares among. Yes, ma'am?
So could you still find the grand mean by just summing all the variables?
Oh, yeah. Yep. So there are two ways. You can sum up all the variables and divide by the total sample, or you can sum the weighted means divided by the total sample size. And you should get the same answer. Yeah.
So I know for among, it's like the entire formula for finding it is the sum of the sample means, the sum of the squares of the sample means minus the grand mean.
Weighted by the sample size.
Right,
Multiplied by the sample size.
And then, so for within, and then what's the equivalent of that?
So within, well, it's less simple because you have two sums. So well, let me do it the way your book does it. I refers to the treatments. J refers to the observation within a treatment. J varies from 1 to n. I varies from 1 to a, where a is the number of treatments, and n is the sample size within samples. So what you do is, within treatment 1, you take the first value minus the mean of treatment 1, square it, plus the second value in treatment 1 minus the treatment 1 mean, and square it, plus the third variable in treatment 1 minus the mean of sample 1 squared. You do that for all of sample 1, and, sorry, you do that. Let me do it this way. You do that for all the observations within sample 1, and then you move on to sample 2 and sample 3, and then treatment 1, treatment 2, and treatment 3, and you then do that across all of the different treatments that you have. So you're summing within a treatment, but then you add all those things up across treatments. So there's two summations. You sum this all for a single sample, a single treatment, then you do it again for another treatment, then you do it again for another treatment for however many treatments you have.
So is that X or I?
That's a subscript ij. I erased the j when I erased to make the 3's. Yep, so these are treatments. So each time you change treatments, the number here changes.
Right. And then, so could you theoretically calculate that value by, I find all the sums of squares for one treatment, find all the squares for two treatments, and then add those two together?
Yeah, that's exactly what I do. Yeah, that's, so.
Let's say, when you first had read that, I was so confused.
Oh.
Now that you just said like that makes way more sense.
This is why I tell you don't try and do this by memorizing formulas. What you do is you take this minus 17.1, square it, minus 17.1, square it, keep doing that all the way to the bottom, add all that up, that's 149.2.
Just sum those 5 across the bottom.
Minus 59.3 squared, minus 59.3 squared, all the way down to minus 59.3 squared, add all those up, 24.1. Add those across, 245.5. Yeah. Don't do this. Stop it. It's nice. It's not, well, it's not nice. It's pretentious. It's confusing. I could teach this by just giving you this and say, go to it. It's all there for you. Doesn't that make a ton of sense? Yeah, it's just symbolic math. All it's basically saying, well, and now it's hard to read because I've written all over the screen. The mean, add up all the x variables, divide by the number of variables that you have. All the x values, divide by the number of values that you have. The sum of this is if j equals 1 to n, it's basically saying, you have n values in here, so you sum across within this particular treatment, treatment I, which is treatment 1, you sum value 1, value 2, value 3, value 4, and value 5. See how this is ij? I is the treatment, j is the value within the treatment. And so this is basically just saying for all these values within treatment 1, it's just the value minus the mean squared all added up. This is the sums of squares within for this particular treatment, but then you do that for this treatment, this treatment, this treatment, and this treatment, and that's what gives you sums of squares within, because you've done that within each treatment, but then you've done that across all of the treatments. Okay, so this is just that, but then you do it for all treatments, which is what that second summation is. So you can learn the equations. You can write them on the board. If your parents ask you what you're learning in school when you go home for spring break, you can say, oh, let me show you. I'm going to write the equation for sum squares within. But it's much more practical to think of this not even as an Excel sheet. It's much more important to think of it as what the different forms of variation are. So now that you've done the hand calculations, this might resonate a little more with you. What is sums of squares within? Sums of squares within can be calculated one of two ways. Well, no, sorry. Sums of squares within can only be calculated one way. How far is this from the mean? Squared. How far is this from the mean? Squared. How far is this from the mean? Squared. How far is that from the mean? Squared again, because you have two of those. How far is this from the mean? Squared. How far is this from the mean? Squared. How far are these three from the mean? Squared. How far is this from the mean? Squared. That then takes care of the control. But then you have to ask, well, how far are these two from the mean squared? How far are these three from the mean squared? How far is this from the mean squared? How far is this from the mean squared? How far is this from the mean squared? How far are these from the mean squared? That takes care of the 2% glucose, etc., etc., etc. If you know conceptually how to do that, you can eventually write a formula for it. But just seeing the formula doesn't necessarily mean that you conceptually know what's going on. This is the variation within samples because you're looking only within the particular sample. Okay? That tells you conceptually what it's doing. What is sum squares among? Oh, I don't have it for that. Sums of squares among looks for how does this mean compare to the grand mean squared? How does this mean compare to the grand mean squared? This mean compared to the grand mean squared? This mean compared to the grand mean squared? This mean, can't see because there's a glare, compared to the grand mean squared. That's the means minus the grand mean squared, but is that sufficient? No, because the samples may be different sizes, so we have to weight it by the sample size. Add those things all up, that's your sums of squares among. If you know sums of squares among, you know sum squares within, you can calculate sum squares total because that's just that plus that equals that. Okay? But you can check your math here. How can you check your math? How do we calculate sum squares total? We can calculate it this way. What's an alternative way of calculating sum squares total?
Do we divide by the sample size, by the way?
Nope.
The population size?
Nope. That's where degrees of freedom come in. So that's where when we go from sum squares to mean squares in the ANOVA table, where we're correcting for sample size. How do we get sum squares total? We don't compare individual data points to the sample mean. We don't compare means to the grand mean. What are we comparing? Not
Every
all,
data point to the grand mean.
not all means together. We've already kind of done that by comparing them to the grand mean. We compare each data point to the grand mean. So the total variation is sum squares total. That's what is this whole variability altogether. Well, if this is the variability within the sample, it's the mean within the sample and how the individual data points vary around that mean. If we want the total variation, we need to know the mean of the total experiment, which is the grand mean, and then we want to know how each individual varies from that grand mean. So how does this vary from that squared? How does this vary from that squared times 3? How does this vary from that squared? This vary from that squared. This vary from that squared. These two varied from that squared times 2. This one from that squared. This from that. This from that. This from that. All squared. This from that squared. This from that squared. This from that squared. For every treatment. For every data point in your data set. So when you're doing this all by hand, especially if you're doing it in an Excel file, which is sort of by hand, you can calculate this and this and find that, but then go ahead and just calculate it as the deviation of each data point from the grand mean, and make sure that sums of squares total done this way is the same as sums of squares total done the other way. Check your math. Some of you on the test would have gotten your chi-square statistics correct had you done something that I stressed to you the Monday before you took the test. You took the test on Wednesday, right? Yeah, I told you, remember that your expected values should always add up to the values in your table. And a number of you had expected values that did not add to the values in your table, which should have told you that there's something wrong with the way you were calculating your expected values. Once again, harping about the test, but the grades were actually pretty good. But for some of you, you struggled with how to calculate expected values. Yeah.
You have a test back today?
Yeah, I've got them right there. Matter of fact, I'm about to stop so I can give them back to you. But don't get distracted, because I asked you at the beginning of class if you had any questions about how to do an ANOVA. Guess what we've done? Well, we did a little bit of R. Well, I asked you after we were done with R if you had any questions about ANOVA. What have we done? We've spent like the last 40 minutes talking about questions about ANOVA, which is good. I'm happy about that. Think about what the different forms of variation are. We talked about this second way of measuring sums of squares total. So you could certainly write this out as each individual value minus the grand mean squared, summed across all of the values within each treatment, and then summed across all the treatment levels that you have. But this is just an equation that says, do this. I'm never going to ask you the equation. I'm never going to give you the equation, except as a reference. Know how to do it. Yeah.
I had a question on the slide where you had the answers. You had a p-value, and I was just wondering what that was.
We haven't gotten there yet.
Okay.
Yeah. So you shouldn't be expected to know how to do that. So let's go back to... So what you do once you have the sums of squares, remember that sample variance is simply the sum of the squared deviations from the mean squared divided by the degrees of freedom. In this case, the degrees of freedom is the sample size minus 1. So this is the sample variance for a single sample. This is within sample variance. So this is the sums of squares within for a particular sample divided by the degrees of freedom for that sample. Now if you have sample 1, sample 2, sample 3, sample 4, and sample 5, you have this for sums of squares within for sample 1, degrees of freedom for sample 1, some squares within for sample 2, divided by the degrees of freedom for sample 2, etc., etc. These degrees of freedom are n minus 1, n minus 1, n minus 1, n minus 1. So it's basically the entire sample of the whole thing, which is 50, minus 1, 2, 3, 4, 5, minus 5, which is essentially the way of saying the big N is the total sample across the entire experiment divided by, or minus the number of treatments that you have. But that's just these degrees of freedom added up in the same way that the sums of squares within is just the sums of squares within for each one added up. So in the sums of squares within category, we have the total sums of squares, the sum of all of this variation within samples. We divide it by the degrees of freedom. So the mean squared value, that's what MS stands for, the mean squared is simply the sums of squares within divided by the degrees of freedom within. Same idea, just across multiple treatments rather than just dealing with a single sample. The mean squared is just the sample variance for all treatments. It's just that. We know how to do variance. The sum squares among is very similar. It's the squared deviations of the means from the grand mean squared, and then you divide that by the degrees of freedom for treatments, which is 1 minus the number of treatments, so that the mean squared is simply the variance that is due to treatment. It's just another variance estimate. I remember when I first introduced this on Wednesday, this is the analysis of variance. Why is it an analysis of variance rather than an analysis of means? Because we're using an analysis of variance to tell the differences between means. Why is it not called the analysis of means? Because what are we comparing ultimately? Well, we're ultimately making decisions about means, but what are we really comparing? This is a variance estimate. This is a variance estimate. We're basically asking how much variance is due to treatment versus how much variance is due to just random variation within samples. It's an analysis of variance because we gain insight about what the means are by looking at the variances. The F statistic is the statistic that you actually look for significance. And the way you find that is you divide the mean squared among divided by the mean squared within. That divided by that should be 49.37. And then that, for this many numerator degrees of freedom and this many denominator degrees of freedom, you can look it up in a table and it will tell you what the p-value is. Or look it up in a table and tell you whether your F statistic is big enough to be significant. I actually looked it up. Well, actually, I calculated it in R. But you evaluate this F statistic with this degrees of freedom in the numerator and this degrees of freedom in the denominator. They're called numerator and denominator degrees of freedom because F is the mean squared among divided by the mean square within. And so the degrees of freedom are the degrees of freedom among and the degrees of freedom within. So this is the numerator, and this is the denominator. And so in a table, it will ask you for the numerator degrees of freedom and the denominator degrees of freedom. And those are that's the row that you look for, or the cell that you look for. So as this gets big, and this is small, this gets big. The bigger F is, the more likely it is that there's differences in your data set somewhere. If this is small, and this is big, this is small, and there aren't any differences among your means because the variation that is due to differences among the means is really small relative to just the random variation. That's how it works. All right. You've done that on this data set. Homework for Monday, do it on this data set. These are ticks on different hosts. This is how long the tick is. So these are basically just lengths of the tick for different hosts. Different hosts had different numbers of ticks on them. This is now something where there are different sample sizes for each host. So you need to make sure that you're weighting your means appropriately when you need to be doing that. Tests. The high score on the test was 102, which means the person scored perfectly and got the 2 points of bonus. The low score was 67. The mean score was 82.9. Why am I having trouble writing things? Just a couple of notes on how it's graded. One of the reasons it takes a long time to grade these is when you make a mistake in a series of calculations where things that come after are dependent on things that come before, what I have to do is I take what your answer was where you messed up, and then I work through the rest of the problem myself to make sure that the future answers that you get, so that that mistake doesn't cascade through the rest of your problem. So you'll see that I do that. I'll take off 1 point here, and the rest of your values won't match what is on the key, but I counted those correct because they're correct given the incorrect calculation that you made partway through it. I don't like you make a mistake early in a set of calculations and then that destroys you for the rest of that particular problem. Unless you just really botch the math altogether, and then there's no hope. And unfortunately, I don't actually know your name still because I haven't really seen your faces all semester. Will Bailey. I'll post the Trenton. He's not here. Blaine, I know some of you. Matthew Chapman, not here. Mallory. Claire. Haha, I fooled you there for a minute. Cole, I know Cole. Joseph, not here. Sabrina is not here. Karis is here. Rachel is here. Tyler. Elizabeth. Austin. All right, if you have any questions on how it was graded or what your grade was or anything else, just let me know. I now have a photo roster for you since I can see your faces. I will learn your names over the next week. Which means you also can't hide because I'll call on you by name on Monday about how well you worked out this problem. Yeah, you too. See ya. $100? Yep. The person who got 102 did perfectly and then got the bonus score. Right. Yep. Mm-hmm. Yeah.